the lights a little here. Okay. So, Dalton's law of partial pressures. It's actually super straightforward. All it says is that if you have a mixture of gases, the total pressure is equal to the pressure of gas 1 plus the pressure of gas 2 plus the pressure of gas 3. We call those partial pressures. So this would be the partial pressure contributed by gas 1. Hopefully this makes sense because the pressure depends upon the moles of gas, yes? So if you have, 10 moles of gas 1 and 10 moles of gas 2, the partial pressures of both will be the same. Does that kind of make sense? Because they'll both bang into the walls with the same energy. Yeah? Okay. So let us, now it says watch, because in theory there's supposed to be like a little animation, but I couldn't make it work. So I was like, let's just go here. So here we have a large glass flask. Here it is empty. Here we have 3 atmospheres pressure. And then then that's our red gas. Okay. 3 atmospheres. And then we attach the blue gas, and then we add the blue gas to a final pressure of 5.3 atmospheres. What is the partial pressure of the blue gas? 2.3. Easy? We like this law? Yeah, okay. (2.3 atmospheres. The final mixture contains more molecules of which gas? Red or blue? Red. Excellent. Okay. Dalton's law can also be used another way. Measuring the volume of a gas can be difficult. You can't just pour a gas into a graduated cylinder because the graduated cylinder is already filled with air. So do you know if you're displacing the air? How much is due to the gas that you're pouring in there? Is that gas lighter than air, in which case it's not going to pour anyway, right? So we have all kinds of problems with this. So we need a gas collection tube. Okay, if you do not have a gas collection tube, you can also use a graduated cylinder. But the trick is that if you use a graduated cylinder, you're going to fill it with water and then turn it upside down. Let's figure out how that works. Okay, a gas collection tube is also known as a eudiometer. I don't think that you will have to know that name. Okay, but that's what they're called. So first of all, we're going to have a little simulation here on paper of producing a gas. First of all, let's complete the following equation. If we heat some potassium chlorate, what are our products? Yes. KCl plus O2, yes. And the state of potassium chloride is solid, and O2, of course, is a gas. So we're going to be looking at the collection of the O2 gas. All right, so here's our little setup. All right, and this is our test tube. And this thing here, right now, it's open side up. This is a gas collection tube. also known as a eudiometer. And you can see it has markings all along the side in milliliters or something like that. I'm just going to go grab one so you can see what they actually look like. So you can see they really look a lot like a burette in terms of their shape and length, but rather than having a drippy thing at the end, they're closed at the end. Okay, so that is a gas collection tube. And then over here, we just have a container filled with water. So that could be a beaker. It could be, sometimes they have one that like has a, up near the top, sorry. Sometimes they have something with a little outlet up at the top. So if it starts to, if the level of the water starts to get too high and wants to like go over the top, it'll actually go out the side, and you would have this like over a sink here, right? So any excess water would just go out into the sink, so you wouldn't have to worry about like overflowing onto your desk or anything like that. This device here with the little doodad out the side is called a pneumatic trough. Again, I don't think you need to know that word, but I'll write it here anyway, just in case. Pneumatic trough. That just looks like such a weird word, but there we are. I guess it's like cough. All right. So in our test tube, we're going to put our potassium chlorate, KClO3. And we are going to fill the gas collection tube, the eudiometer, with water. And we're also going to put a stopper on the top. Sometimes, if the opening is small enough, we don't bother with a stopper and we just use our thumb. So you can turn it upside down without the water flowing out. Okay? And eventually what you're going to do is you are going to stick it into the beaker with the water. Of course, this wouldn't be a very good beaker because I can hardly fit my hand in it. Yeah? But let's say I could. Let's say the water was up to the very tippy top. I could let go of this as long as the tip is under the water, and the water will stay in the tube. Would we like to see it? Okay. I'll get a bigger beaker so my hand will fit. Okay. Sorry, we forgot. You won't walk about it. Okay, I've got a really big beaker. This one should fit my hand aside. Those of you at home will just have to imagine this. Okay, and I'm going to fill this up with water all the way. Okay, so that is full of water. There's a little gap at the top. I'll just finish filling that up. There we go. Okay, and put my thumb over the top. Woo. And then, do you see how it all stays? Okay, and I would have a clamp here or something to hold it so it doesn't like fall over. All right. So we fill that with water, we've got that, and then we turned it upside down and we removed the, so we invert the U-diometer. The U-diometer, which is also known as a gas collection tube, if you prefer that name because it's less, weird. And we remove the stopper. And we also have up here, we now have a stopper with a hole. And what we would do is we would put, I guess I could draw it over here. I'm going to make it just bigger so you can see. If this is the top of our test tube here, all right, your stopper would be in it. Okay, but in the middle of it, if I did a cross section of it, there would be a hole. Okay, obviously it would not actually reach across the entire test tube because then it would be two pieces instead of one piece, but it's just a single hole in the middle. And what we would have in there is we would have some glass tubing. Oops. Okay, sorry. And then on top of that glass tubing, you would put a rubber tube, very much like the one that is on the sink right here. Okay, so you would stick that glass tube, and then you would put the rubber tube okay, which all looks very complicated, but when you have it all together, it just looks like this. Yes? So you have a rubber tube attached to your test tube, which will allow the gas to go this way. That makes sense? Okay, cool. So now the gas is going this way, and it is going to... Hi. You can be here. I'm just having a tutorial.
Sure. Is it okay for basically if they grab a review and just
Oh yeah, absolutely, no problem.
involving the ions and the atoms and the charges. Remember the one?
Yep.
The long one?
Yep. That's the one there. There you go. Okay, so now we've got this here, and now what we're going to do is we are going to make our reaction happen. So we are heating the KClO3, and it is giving off, of course, the O2 gas. All right, and the O2 gas goes in here, and it's going to start bubbling up. And when the bubbles reach the top of the tube, you're going to start to get, you can see there's a little gap up here. Is there a little gap? Yes, there is. It's really hard to see. There's a little gap up there where we have O2 gas.
So that's the water level.
Pardon me?
So the water level in the beaker rise.
The water level in the beaker will rise, yes. Okay, because the water is, as the gas displaces the water moves out into the beaker. Okay, so there's our O2. And then we have more bubbles. And then we have yet more bubbles. And eventually the reaction is complete. All right, and what we can see here is that the water level in the gas collection tube is right here. But the water level in the gas in the beaker is higher. Right now, which pressure is greater? The pressure of the oxygen or the pressure of the atmosphere? The oxygen, because it's pushing down more, right? And we want to know what the pressure of the oxygen is. So what we're going to do is we are going to, so P of atmosphere is less than P of O2. Now, the nice thing is that if we have, I'm just going to let some out of here. See if that works. Yeah, it does. Oh, too much. Oh, no, that's okay. Okay. I can actually, do you guys want to come like closer so you can look at it? Come closer. You won't be able to see it from there. All right. So what I'm going to do is I'm going to just lift this up until it's at the same level. Yeah? And then the pressures are equal. What that will do is because I'm equalizing the pressure, the volume of the gas will change a little bit. You won't be able to see a huge difference, but there is a small change in the actual volume of the gas. Okay, but now we know that if we're at sea level, what's the atmospheric pressure? 1 atm. So what's the pressure of the O2? Right now? 1 atm, because they're equal. Yeah, so that is a key step in the whole process, is that you have to raise or lower the eudiometer until it is stable.
By raising the eudiometer and lowering it, what does that change?
It changes both the pressure and the volume. The volume changes small, the pressure changes small. Okay, but it does make a change. Okay, all right, you can go back to your seats now. So we raise the gas collection tube. And now you're seeing the advantage of the word eudiometer, because it is indeed shorter than gas collection tube. Okay, but not by a lot. Raise the gas collection tube until level of H2O tube equals level H2O beaker. And now our P atmosphere and our PO2 are equal. So now we know the pressure of the O2 because we use a barometer to figure out what the atmospheric pressure is. If we don't happen to be at sea level, we can use a barometer, okay? So we know the pressure of the O2. We can also then use our eudiometer to measure the, what can we measure on here? What are these markings? Volume. We can measure the volume of the O2. So now we know the pressure of the O2. We know it's not a very good highlighter for green. We know the volume of the O2. And what else are we going to put in there? That is a thermometer. And that means we are going to know the temperature of the water. Now, why the heck is it important that we know the temperature of the water? Well, if you think about the gas in this tube, it contains O2 gas, but what have we been learning about for the past like 2 or 3 weeks? I don't know if you have any recollection whatsoever, because there was a spring break in there and all kinds of things. We have a liquid, and above that liquid, we have an empty space that is closed on the top. Yeah, there's vapor pressure due to the water. So it's not just O2 in there. There is also water vapor, okay? Also, that only has one L.
Very small amount.
It's quite small. Yes, it's not a lot, okay? So now what we have in there is now we have a mixture of gases, yeah? But if we know the vapor pressure of the water, vapor pressures of water are given in, you can look them up in tables. So every temperature, the vapor pressure of water is different, right? So what you're going to do then is you are going to look up the vapor pressure of water. At that temperature. All right, and so it turns out that this pressure over here, this one over here, is not just PO2, it is also PH2O in the thing. And we will talk next week about how we go about extricating the oxygen from the whole thing. Homework this week, do page 65 from last day's stuff, okay?